Hi, I'm Matt Russo, and this course is Music and Astronomy, exploring rhythm and harmony in the cosmos. Now, you might not think music and astronomy are related, and I didn't. I'm a musician and an astrophysicist, and for the longest time I thought of these as two kind of separate worlds. And that all changed last year when scientists made a very interesting discovery, which I'll tell you about today. It turns out that this idea, though, of a connection between music and astronomy is very old. It's over 2,000 years old, first proposed by Pythagoras. You may recognize his name as the founder of the Pythagorean theorem. And he said, there is geometry in the humming of the strings. There is music in the spacing of the spheres. And so he literally believed that the motions of celestial objects, like planets across the night sky, was creating music. And not just music, but harmonious, beautiful music. Of course, you probably don't hear anything, and so he said, the only reason you can't hear it is because you're just so used to it. You always heard it, you always will hear it, and so your ears kind of tuned it out. So not everyone was buying this idea of the music of the spheres, including big names like Aristotle. So he said, it is a very beautiful idea, but not only do I not hear anything, if the planets were actually making noise, it wouldn't just be deafening, it would be destructive. The noise would just shatter us all. And we're still here, so there is no music of the spheres. The planets do not make literal music we can hear. It turns out they were both right, and I'd like to explain how. But first, we have to answer this seemingly silly question. What makes music musical? And I just mean, why is it that some notes sound relatively good when played together, and some notes sound terrible? Why are some instruments in tune and some are out of tune? And why can you even make 12 notes at all? So 12 notes on a piano, why aren't there a million or an infinite number? What's going on there? The answer was actually found by Pythagoras himself. He found that the secret to musical harmony is actually very simple mathematical ratios. Here's what he meant. If you take this string on the far left, imagine this is a giant cello string. And someone's going to bow it, and it's going to vibrate back and forth really, really fast, faster than you can see. That'll make some kind of low note, like this. But if you cut that string in half, each piece will actually vibrate twice as fast, and it'll produce a related note. That's an octave. Or cut it in 3 parts, or 4. And so on. So all of those notes sounded relatively pleasing when played together. They're all related notes, and that's because there's very simple ratios between how fast they oscillate. 2 for every 1, or maybe 3 for every 2, and so on. The other thing you need to know about music is that it's composed of pitch and rhythm, but it turns out those are actually the exact same thing, just processed by your brain differently because they're happening at different speeds. I can show you this too. That's a rhythm, happening maybe once a second or twice, but as you speed it up, it becomes a pitch. So it's the exact same information happening at different speeds. If it happens less than 20 times per second, your ear says, I'm listening to a rhythm. As soon as you hear it, as soon as it's happening more than 20 times per second, your brain just kind of flips and says, now I'm hearing a pitch. Same information processed differently by your brain. And so what does this have to do with astronomy? Well, here's that big discovery from 2017. It's the TRAPPIST-1 planetary system. Astronomers found 7 planets all orbiting a nearby red dwarf star called TRAPPIST-1. All 7 planets are Earth-size. They're very close to Earth size, and we think that at least 3 of them have the right temperatures to support liquid water, and of course, possibly even life. So this got everyone excited for various reasons. It's relatively close by. We have a chance of actually detecting what's going on in the atmospheres of these planets in the next few years. And it also looks like a nice place to visit. I'll show you that in a minute. But first, you have to understand that this system is bizarre by our standards. It is a miniature solar system. Here are the orbits of the inner rocky planets in our solar system: Mercury, Venus, Earth, and Mars. And to scale, the entire 7 planets of TRAPPIST-1 are tucked right in between there. They're huddled right up against their star. I'll have to expand them by 25 times just so you can see their relative orbits. And it turns out that TRAPPIST-1a, the star, is actually not much bigger than Jupiter, our planet Jupiter. It's a very small, cool star. And the TRAPPIST-1 planets orbit just a little further in most cases than the moons of Jupiter. So Jupiter and its moons is a much better analog of TRAPPIST-1 than our own solar system. And so here is what astronomers and artists thought it might look like on one of these planets. So you can see lots of water. We now know that several of these planets have a ton of water. Some glaciers. Their sun would be about 10 times bigger in the sky than our sun is in our sky. The other neighboring planets are about twice as big as the moon in our sky. So you could possibly see other continents and maybe city lights on the next door planet. But then astronomers refined their measurements. There were some new studies that came out to try to figure out what's actually going on these planets. What might they look like? And the artist renderings changed by just a little bit. They started to look a little more like this. So instead of being a peaceful, habitable planets, astronomers found that at least the inner ones might have molten lava surfaces. They may be being cooked from the inside until they melt. And TRAPPIST-1a, the star, has very damaging X-rays, which is bad for life, and it also strips off atmospheres, so maybe some of that water couldn't survive long enough. But then, of course, science progressed, and we refined our measurements even further and did more and more careful studies and found out that, at least in some cases, it would look pretty similar to this, we think, on some of the planets in some of the locations. But here is what got me really excited about this system, and was the genesis for this entire course in a way. TRAPPIST-1 is what's called a resonant chain. And so all that means is that for every 2 orbits of the outer planet, which takes about 40 days, the next planet in orbits 3 times, and the next one 4, and then 6, 9, 15, and 24. And so they're all working together, completing orbits like clockwork. They're all kind of communicating to keep themselves locked in these very simple patterns. So you see simple ratios like we saw before. 3 orbits for every 2, or maybe 4 for every 3, 3 for every 2, and so on. And so I realized that there are musical patterns here. It turns out that these planets are orbiting, if they could produce music, if there were air so that we could hear the sounds, the notes would be below our human hearing range. So first we have to speed up their motion by thousands or even millions of times so that we could actually hear the rhythms and pitches of this system. And when you do, you'll find that this system and this system alone, so far, actually makes musical harmony. It's the most musical system we've ever found. And the best way to understand that is to listen to it. What does this sound like? And so I created a numerical simulation of this system, and it's going to play 1 note for every orbit of each planet. And once I chose that first note, all of the other notes and rhythms you hear are coming from the planets themselves. It's their harmony, their rhythms. I'm just putting it to a piano sound so you can hear it. And once all 7 planets are in, you're going to start hearing drums. And the drums happen every time 2 planets pass each other. That's when they kind of give each other a gravitational tug. And so I played a drum for every time that happens. And setting up those simple rules, running the computer simulation, this is what comes out as the music of TRAPPIST-1. crackle you heard at the end was actually the light of the star directly converted into sound. That's actually how we discovered these planets, by looking at slight variations in the light from this star. And that's because every time a planet passes in front of the star, it gets a little dimmer. And so this is the most musical system ever discovered, and you might wonder how this happened. And it turns out that it's very important that it did happen in the first place, because if you just put these planets roughly where they are right now in their orbits, they're huddled really close together. And so after a short amount of time, they start tugging on each other and start crashing, or some planets might get ejected or thrown into the sun. And so you need something to keep this system stable. They're too close together, interacting too much. So we have a problem here. It's a mystery that had to be solved. It turns out that when I was converting this system into music, I found out that the astrophysicist in the office next door to me was solving this mystery. And here's what he found. When you go to see an orchestra, the musicians come out. They can't just all start. Right? First, they have to get into the right places, and then importantly, they'll have to tune to each other. And then you need a conductor to make sure they're all in sync. And so that's exactly what happened to TRAPPIST-1 early on. Here you can see TRAPPIST-1, the planets are forming inside a disk. That's how planetary systems form. They're orbiting inside a disk. And the disk gives them kind of like a drag force, and it lets them shift their orbits. Maybe they orbit a little closer or further from the star. And so this system was able to shift their orbits and finally tune themselves to each other, tuning themselves in the same way that an orchestra tunes. Every planet slowly adjusts its orbit until it's in tune and resonating with its neighbors, until they form musical harmony. And it turns out that this very precise configuration of their orbits is what keeps them stable. They're always in the right place at the right time. And so this is the most musical solar system, but after I did this, I realized we have an entire universe full of rhythms and harmonies, things that we can hear, different kind of cycles in nature. And there's many ways we can hear the music of that, directly or maybe indirectly, maybe adding a little creativity along the way. So for instance, you can take the stars in the night sky and represent their colors as musical pitches in a scale. So in this case, the cooler, redder stars are the lower notes. The hotter, bluer stars are the high notes. And each constellation will make its own unique melody. You can also take other types of waves in the universe. These are actually magnetic waves caused by lightning strikes in Earth's magnetic field, and you can find a way to convert them to sound so that you can hear them. Or you can listen to a drum beat played by Jupiter's moons, which are also locked in resonance, similar to TRAPPIST-1. Or you can hear a scale that the moons of Saturn play in the rings of Saturn. The rings are a giant musical instrument. Or you can map data. This is one note for every planet we've discovered orbiting a different star. And the pitch tells you the type of star it's orbiting, hot or cool. Or you could play a note for every galaxy you'd find if you could fly away from our home, the Milky Way, towards the edge of the observable universe. And as we're flying out in space, we're also flying back in time towards the Big Bang. And that is the tone of the entire universe shortly after the Big Bang as it was expanding. It was resonating, just like a tuba. And so This may be fun and interesting. It may give people a different way to experience the universe or to understand astronomical systems. But for me, it's also important that we're opening up astronomy to a wider audience, namely people that are visually impaired or blind or partially sighted. And so I've collected all of those sounds and more and created an audio planetarium show called Our Musical Universe. And so we have frequent visits by groups of the visually impaired. So there's a social aspect to this course as well. And the way the course is structured is we're going to start by learning about orbits and solar systems. How did we discover that our solar system is heliocentric, so the planets orbit the sun, because that'll let us make music out of the solar system and other solar systems. We'll have to learn a bit about how waves and sound even work. How do musical instruments make sounds, for instance? What are sound waves? How does your ear hear them? How can you make them with a computer, for instance? We'll dig into music as well. We'll learn some basic music theory. We'll create our own musical compositions and maybe perform them too, if you happen to play an instrument. But the goal of the course is to integrate all of these fields into one, and that is in the form of a sonification project. So sonification is what we've been doing today, converting data into sound so we can hear it rather than see it or look at it in a chart, for example. I call that making space music. And so every student is going to create their own song using data from space in some way. An image of space, information about planets, something from space that we can use as inspiration or directly the data to convert into sound or music to express something about, ourselves and things that we are interested in and connected to. And at the end of the term, we're going to have a final presentation where everyone shares the work they've done, the music they've created and what it means and how it connects to astronomy, the astronomical system they've studied. And we're going to do this also in public. So we're going to share our music with the public audience and invite people that are visually impaired to share a little bit more of astronomy with them. Thank you.